p partial with y should give you 2x. Then, separate step, q's partial with respect to x. Q's partial with x is 2x. So since those check out, this is a conservative vector field. And I'll abbreviate vector field VF. So in 2 dimensions, it's easy to check. Just take your 2 components, take those one partial derivative each. First component is partial with y, second component is partial with x. And see if those match up each other, okay? Now, here's the real fun thing. How do you find that potential function? So in other words, we want to find a little f of xy function such that its gradient, which again is still constructed this way, is the same as the components of this vector field. Okay, so in order to find that potential function, this vector field already is the gradient. We need to come up with a way of reverse engineering the gradient process to go back to the function it came from. Okay, so you're mixing derivatives, well, you're mixing partial derivatives now with partial antiderivatives. Because in order to check for conservativity, you have to take a partial derivative to see if that criteria is met. But now, in order to do an anti-gradient, to go backwards from the gradient, this thing is already a first partial with x, which means I should do this. Integrate the p component of your vector field, and again, let me put those letters there so you remember who's p and who's q. I need to integrate p with respect to whom? With respect to x, because if it's already a first partial with x, if you do its antiderivative with respect to x, then that'll tell you what the potential function, the little f, should look like. So I'm integrating 2xy plus 3 with respect to x. So again, now you're doing antiderivative rules, okay? Remember, your power rule derivative is n x to the n minus 1, but your power rule antiderivative is x to the n plus 1 over n plus 1. So watch out for your mixed match, derivative versus antiderivative rules that you need. So here's the thing. 2xy, y is a constant, and x is what you're integrating, so 2x will become x squared. Y will be left alone. Plus 3 will become plus 3x. Now here's where you got to be careful and pay attention. I always pay attention because I say some really cool stuff. But should I put a plus c here? In other words, I do need to, but is the plus c going to stand for a constant necessarily?
It's a different level of your vector field, isn't it?
Well, no, we've already left the vector field. We're back to the scalar function level now because we've done the antiderivative. So what we're putting here are things that potentially contribute to this thing. In other words, this thing should have some of this in it. But if I just do an antiderivative with respect to x, what other things could be playing the role of a constant?
Y?
Yeah, anything involving y or just any number. So instead of putting a plus c here, well, let's do this. Let's just say plus some g of y. Function notation. The plus c here could have been any function that depends only on y. Because if I take this thing's partial with respect to x, it should take me back to this verbatim. And it does. 2xy plus 3 plus 0. Because that would annihilate when you take the partial with x. Same idea when you do this thing's partial antiderivative. You want to also compare your result here with the antiderivative of q with respect to y. Since q is the first derivative with respect to y, you want to take that antiderivative backwards to see what the potential function could look like from it. So now I want to integrate x squared plus 5 with respect to y. And so x squared is a constant. These are both constants with respect to y. So that technically gives me x squared y plus 5y. But then in this case, plus some other, I don't want to be too liberal with the f, because f's already kind of committed to this guy's name. So I'm just going to go ahead and call it some h of x. So your constants here aren't just going to be plus c's. Your constants are going to be functions of the other variable that you're integrating with respect to, you see. So tucked into this two bits of information, that's what our potential function is. So We've got it right there in front of us. If I take either one of these statements, I could use this first statement right here, and it is my potential function. But what you got to do is keep an eye on this too, to make sure that all the parts that you need in this potential function are there. So if I just go left to right, the potential function has to have x squared y plus 3x, and then maybe it has some function of y in it. Does this suggest what that function of y has to be?
5y.
Yeah, because, I mean, you could use either one of these two statements to represent your f of xy function. The first one there, that first line right there that I got from integrating p, tells me I want x squared y plus 3x, and then this is why you want to also integrate q. If I look at these two together, they both have the x squared y, so I know I should definitely have that there. This one doesn't have the 3x, but it has a 5y with it. So that leads me to believe that g of y that's referenced right there has got to be plus 5y. Now here's the other kicker. There could have been a plus 10 or a minus 3 or a plus pi or something like that. That doesn't matter. It's okay. As long as you have all the variable representation here, that's the main thing. Could we have also gotten this potential function from this statement? Yeah, look at what we integrated for q. We'd still get the x squared y, we get the 5y, and then we have some standalone function of x. So if you cross-reference that with what's up here, that has to be the 3x. So either one of these is a complete representation of what your potential function is. But you need to integrate both p and q to make sure all the parts that need to be there with the function f are there. Okay? Bless you? Hiccup? I'll bless a hiccup. What the heck? And so that is, well, I'm going to circle it as though I'm confident and I know I'm correct. But what's the ultimate way to check your potential function when you get it? The definition of a potential function is take its gradient. If this is the potential function of that vector field, then that means I should be able to go backwards now, or I guess in this case frontwards, take this thing's gradient and it produced my vector field components. Partial with respect to x is 2xy plus 3. Boom. Partial with respect to y is x squared plus 5. And boom, yes. So you should be able to check your potential function by just doing the regular gradient, and it take you back to the vector field you started with. So do you kind of see why I call this the anti-gradient? You're sort of doing the gradient backwards, going from the vector field to the scalar function, the potential function here. So now that you've done all this work, let's put the FTLI, the fundamental theorem of line integrals, to the test. It says, use the fundamental theorem of line integrals to evaluate the f dot dr line integral for the vector field, and luckily it is the same one we've been working on this whole page. This vector field along this curve, okay? So, according to the way the fundamental theorem of line integrals works, I do need my vector field, and if I know it's conservative, when we spent the whole top 2/3 of this page doing it, if you know it's conservative, then instead of doing it the long way, where you do all the replacements for x and y from the parametric equations and so forth, you could just take your anti-gradient function and plug in your endpoint of the path first, and then subtract it, evaluate it at your beginning point. So this looks like all the other f dot dr, like 3 other ones that we've done since Tuesday night, where you would make the replacements and everything like that, and do the dot product and so forth. But the only thing I need from this path is, what are the endpoints? So I need to know my beginning point. How would I get my beginning point for this path based on what's given there?
Plug 0 into.
Yeah, the beginning point occurs at t equals 0. Notice every time you're given a path that's represented parametrically, those t restrictions tell you where you're going to and from. Okay, you're beginning at t equals 0, you're going to t equals pi over 2. So at t equals 0, just plug that into each component one at a time. 0 plugs in for your x, and I don't mean to screw you up with this. I'm just going to the path as a parametric curve. See, this is what I'm referring to as x equals, and this is what I'm referring to as y equals. The I component's your x equation, the j component's your y equation. So if I plug t equals 0 into both of those, I get 4 cosine 0 for x. I get 5 sine 0 for y. So I'm beginning at the point 4, 0 on this path. And then my endpoint is located at the other t value that I need in my other end, t equals pi over 2. So same idea, take pi over 2 and plug it into both parts of the parametric equations there. 4 cosine pi over 2 goes away to 0, and then 5 times sine of pi over 2 is 5 times 1. So that means you should end up at the point 0, 5. Anybody recognize what the path is? Anytime you pair x with cosine and y with sine, what do you usually get?
Circle.
Circle. If the coefficients are the same, it's a circle. If the coefficients are different, it's an ellipse. So technically, the path you're doing here is going from this point on the x-axis, 4, 0, and ending up at this point on the y-axis, 0, 5. So you're really just traversing 1/4 of an ellipse based on that parametric orientation. So, here's where the FTLI comes in handy. The f dot dr integral here is the same thing as our potential function evaluated at the end point minus our potential function evaluated at the begin point. So we found our potential function right up here. I need to evaluate it at the point, and again, make sure it's end first and then begin last. So end point is 0, 5, and then subtract the potential function evaluated at 4, 0, your beginning point of the path. And so, little asterisk. We figured out earlier that f of xy was x squared y plus 3x plus 5y in that previous problem. So, again, that's just my poor notation there for making a reference to the previous problem. So I want to take a fresh copy of this, plug in 0 for x and 5 for y. So 0 for all these x's wipes out the first two terms. You're left with 5 times 5. So this should give you the value 25. When I do take a fresh copy of your potential function and now plug in 4 for x and 0 for y, so 0 for y wipes out the first and the third term, and then the middle term is 3 times 4. It should be a 12. So you should get a value of 13 for this line integral. Would this one really be that hot of a mess if you evaluated it the long way? If we went back to doing it the way I showed you on Thursday night, before you knew to recognize, conservative vector fields in this fundamental theorem, what you'd have to do is rewrite the vector field See, the original vector field, the I component was 2xy plus 3. So, ooh, purple, cool. You'd have to 2xy, so 2x. So you have to do 2 times 4 cosine t times y, which is 5 sine t, plus 3, comma. And then you have to do x squared plus 5. Remember, because you're replacing the x's and the y's with their parametric equations from your path. So that's where I'm getting the x's and the y's from, is right here. So x squared plus 5 would be 16 cosine squared plus 5. Then I have to dot product this with r prime, which would be negative 4 sine t, comma, positive 5 cosine t, and that dot product produces my integrand. So this times this, you can probably do a u sub there, and then this times this, integrating cosine cubed, you can do it, but yeah, that'd be, I'll say it's a hot mess. It would just be, a little bit more than what we needed space for there. A good bit more than what we had space for there. But if you do it that way, I challenge you to it. I don't want to do it because it's a hot mess. But if you do it that way, you have to be able to get 13. You would get 13 as your value, I promise. Promises aren't good enough. You like to see it later. I don't want to do it now because it would take up a good bit of class time. But I assure you, if you did it the long way, you get 13. But I think finding the potential function was the main hard work here, coming up with that. But that's just integrating your p with x, integrating your q with y, comparing the two results to make sure you see which parts contribute to this g and h. And then as soon as you got that, you're golden. You just need to discern what your beginning and end points are, and then evaluate the end point plugged into the potential and minus the begin point plugged into the potential. I think on a previous test that I've given for this, I would give like a vector field that's really, a vector field that's kind of straightforward, but then the path is some kind of really hot mess involving like, inverse tangents and stuff like that, that really the path itself turns out to be just something that gives you points. And that way, I think I actually put a hint on a problem like this and said it would really come in handy if this is a conservative vector field. And that was sort of their little subtle hint to say, well, okay, maybe the fundamental theorem applies. All right. So maybe I'll afford you that same hint, depends on how much of the Christmas spirit I'm in. So, for 3D vector fields, still, you want to be able to check it for conservativity first to see if you can apply the fundamental theorem. The fundamental theorem extends to 3D as well. If your potential function in that case will be a function of 3 variables, x, y, and z, and then as soon as you know what your potential function is, discern what your end point, your beginning points are, and it works the exact same way. The only extra notch of difficulty, tiny little notch, is the conservativity test that you have to go through for a 3D vector field. And this is the way it works. You're going to name the components of the vector field P, Q, and R now, and since we're in 3D, those will be functions of x, y, and z in 3 space. So those components, to check for conservativity, what you have to do is you make pairings. There's 3 different pairings you can do here. You compare P with Q, you compare P with R, and you compare Q with R, you see? And you want to still do the same kind of partial derivative mixed check, okay? The way you do it when you pick P and Q, P is in the x position, Q is in the y position. So mix those partial derivatives based on those positions. Take P's partial with respect to y, and take Q's partial with respect to x to see if that's true. And then you're 1/3 of the way through with verifying conservativity, because you have to verify it for every pairing you can make. Then if you pair P with R on the end, P is in the x position of the vector field, R is in the z position of the vector field. So I need to see if P's partial with z equals R's partial with x. Then you're 2/3 of the way through. And then finally, the last pairing you can make is Q and R. Q is in y's position, R is in z's position. You check Q's partial with z and R's partial with y. And finally, if that checks out, you've got a conservative vector field. There is another check that, if I have time, I can show you a little bit later. I don't really have time for doing it tonight. But there's a calculation you can do with vector fields called divergence and curl. Have any of you ever heard of those before at some point? The divergence of a vector field or the curl of a vector field?
I heard of curl, but I've no idea.
Curl most likely comes up in a reference of, I'd probably say torque or something like that.
Okay.
When you calculate the curl of a vector field, it's essentially a way of measuring, like if you have a point in space in some vector field, if you were able to put some kind of little 3D paddle there that was influenced by the vectors and causing a spin, the curl essentially measures the axis of that spin. So in other words, over here, if the rotation of the vector field is like this and it causes a spin like this, then that will be the curl direction, okay, the axis of that spin. So on a conservative vector field, the curl always produces a 0 vector. Yeah. But it's a cross-product calculation, and it's got a big determinant, and you have all these components to do. In my opinion, just remembering how you mix and match those 2 positions, like x here with z here, partial with z equals partial with x. That's the main thing. That's the easiest, probably, in my opinion, way to check conservativity. So let's do it with this guy. 3 things to check.
You gotta zoom out.
Oh, do I need to zoom out? Oh, yes, I do. Yeah, I can see what I'm writing. So is P's partial with y equal to Q's partial with x? And if you need to impose your labeling system, feel free to. Place the P and the Q and the R over what they represent. P's partial with y is 2y. Q's partial with x, 2x right there. X goes to 1, so that becomes 2y. And then the e to the 3z goes to 0. So the first check, does everybody see how that checks out? Then you want to check, is P's partial with z the same as r's partial with x. So p has no z in it whatsoever, so everything's constant there. And similarly, r has no x presence in it, so r's partial with x is also 0. So even if they're both equal to 0, they're still equal. So it still fits the criteria. We're 2/3 of the way through with verifying this vector field for being conservative. And then finally, the last pairing is to pair q with r. So q's in the y position, take its partial with z, see if it's equal to r. R's in the z position, take its partial with y. So q's partial with z, we're finally getting to use this exponential expression. E to the 3z's derivative would be 3e to the 3z. Does everybody see how that works out? It's chain. The derivative for e would be e to the 3z. The inner function is 3z, so you have to multiply by the derivative of 3z on the outside. So your full partial of q with respect to z should give you 3e to the 3z. R's partial with y, 3 and e are both constant since they're functions of things other than y. The y in the middle there goes to a 1. So you get, check this out. Okay. So since those mixed partial triplets, triplet pairings I guess, they all equal the same thing, then that means this is a conservative vector field. What? Okay. That's excitement, that's not factorial. It's just me being yay. Okay. So, what's the potential function? Done the same way. If the vector field's already the gradient, then that means, P, Q, and R in that order are the same thing as some potential functions partial with x, partial with y, and partial with z. So if you write that pairing, that'll help you remember who gets integrated with respect to whom. Okay? So I should first integrate p with respect to x. So my p function is just y squared. So that's entirely constant with respect to x. That should give me x times y squared. Now, what's my constant going to be in this case? Who would go to 0 when I take a partial with respect to x?
Y and a z.
Any function that depends on y, any function that depends on z, or any function that depends on y and z. So the best thing to say is just kind of collect them all together as some function of y and z, like this. Okay. And then again, you'll want to cross-reference with the other ones to make sure you have everybody present for your potential function when you're done. So I integrate q with respect to y now, and that'll do the anti-gradient from q. So integrate, boom, there we go. 2xy plus e to the 3z with respect to y. So I've got a presence of y right there in that first part. That y should become half y squared, so that cuts the 2x in half. So that should become xy squared plus e to the 3z is constant with respect to y, so I just multiply it by a y. E to the 3z times y. And then plus, sorry, I can't color code here, I'm running out of colors. This one would have to be some function that depends on whom? X and z. Because those would have been your constants when you did a y partial. And then finally, integrate your r with respect to z. So for this one, I'm integrating 3y e to the 3z. And so if it helps, to focus on your variable, I mean, sometimes some people like to pull the constants out to the front. Like, if you want to do this, pull the y out to the front so you see you're integrating 3e to the 3z. And then, I guess the use of that would work here is to let u equal 3z. Then du is 3dz. So you're really going to integrate e to the u. So y e to the u goes back to y e to the 3z. Plus, I'm running out of function names here, plus some other function, I call it k, that since we just integrated z, it would have had to depend on x and y. Okay, y'all with me so far?
Sure.
At least the ones that are still awake are. Okay. So the potential function, we should be able to get a complete representation of this potential function from any one of those three rows after the equal signs and those antiderivatives. So I always recommend going for the one that's got the most bells and whistles to it. This one right here from integrating Q has two contributions right there. These other ones only have one, so that might tell me everything I need to know. Okay, so I know my potential function has to have an xy squared. I know my potential function has to have this, e to the 3zy or y e to the 3z, no matter which way you write it. Now, looking at the other two, are there any standalone functions of just x and z that you see here or here? No, I see a function of x and y there, but it's already counted, so don't count it twice. I see a function of just y and z here, but it's also already counted. So in this case, this guy is 0, because there's no representation of it in the other two antiderivatives. This guy, however, is who?
Y e to the 3z.
That's the y e to the 3z, and this guy has a representation. That's the xy squared from the first one. So not all of them are 0, but if you go for the entry here that has the most stuff in it before you get to your little red constant function, then that's going to contribute the most stuff to your potential function. And in this case, that was it, verbatim, altogether. So that should be the potential function that gives us this, well, don't have to zoom out, gives us this vector field when we do its gradient. So again, just double check real quick. Partial with respect to x across the board is y squared. I component, checks out. Partial with respect to y across the board is 2xy plus e to the 3z. That checks out. Partial with respect to z goes to 0. Y times e to the 3z times 3. So 3y e to the 3z should be your last component. So it does check out. That is indeed my potential function. So now, second verse, same as the first. Once you find the potential function, most likely you're going to be prompted to find some kind of line interval value using that potential function. Use the fundamental theorem of line integrals to evaluate an f dot dr integral for the same vector field we've been working on along any path that connects the origin to the point 321. That was a little bit sweeter than the last one. The last one you had to go through the parametric curve and plug in t equals 0, plug in t equals 1 to get your end and begin point. This one tells you, and again, preposition is playing a really big locative here. Any path that connects the origin to the point 321, which implies the origin should be which one?
0. It's your starting point.
But your starting point, yeah. The origin is 0, 0, 0, but I'm saying more importantly here, that's where we're going to begin. And you're going to the point 321 out in space, so that's where you're going to end. So since this is a conservative vector field, the fundamental theorem of line integrals applies. So instead of me calculating this by coming up with a parametric equation, doing the substitutions, building the dot product and things like that, you just need to do scalar function evaluated at 3, 2, 1 minus my my potential function evaluated at the origin. That's it. So, and again, I'm referencing that function that we found right there. So 3, 2, 1 plugged in for x, y, z. That's going to be 3 times 4 is usually 12. And then 2 e to the 3. So when I plug this in, I should get 12 plus 2 e to the third. And that should look like a 2. Sorry, my 2's look like a z's, but now you see why I put little slash marks in my z's. The origin, when plugged in, that goes to 0, and 0 times anything is going to wipe that out too, so you actually get nothing when you plug the origin in. So the complete line interval value, 12 plus 2 e to the third. What about the statement of this problem? Aside from the 2/3 of the page up above it, where we did all this conservativity check and finding the actual potential function, well, what about just the statement of this problem would let you know, and I guess other than that, lets you know that you could use conservativity in the fundamental theorem. And I know, okay, yes, the fundamental theorem is actually referenced in the statement, but what else in the statement of the problem lets you know?
Any path.
Yeah, the words any path. Any path connecting the origin to here means this is a path-independent line interval. So conservative vector fields offer path independence whenever you're trying to calculate the work. Any path that goes from here to here is going to be the same amount of work. That let you know you have a conservative vector field. So you can do the anti-gradient like this, and then plug your endpoint in minus your begin point plugged in. You feel smarter?
Yes, sir.
Okay, it's good. All right. Expand a little brain. Okay. Next topic. Green's theorem. Green's theorem is kind of handy because it allows you to evaluate line integrals that make a closed loop. All the line integrals I've shown you so far of the different types, you go from here to here. You can have a straight line path, a parabolic path, a semicircle path, or something like that. But if you have an integral calculation, a line integral calculation along a closed loop, that's what this thing's all about. And for some reason, when I print off my PDF, the little circle in my integral symbol is off center. Does anybody have the circle actually centered in your line integral? I guess I just need to change my printer or change my browser settings or something like that, because it should look like this. It doesn't have to have the arrow there, but it should just be a circle that's kind of centered. This one looks like it's sort of, an integral sign with a humpback or a backpack on it or something like that, but it should be in the middle of the integral sign. So sorry about the mismatched notation there. But that's what that symbol means. So like if I were evaluating, and notice this is focusing on the dx dy type of line integral. So if we did this one the way I showed you Tuesday night, you'd have to, essentially you'd have to come up with parametric equations for all four of those paths. And you have to do 4 different line integrals. Come up with a parametric equation here, and it's not too hard. It's a horizontal line segment, so you let x equal t, and let y equal 0, because you're going to stay at y equals 0, and then x or t needs to go from 0 to 1. So it's not too hard to parameterize that. But then you got to plug in your x, plug in your y. What gets plugged in for dx and dy? It all depends on those parametric equations. Eventually dt, but if x, let's say x equals t squared. Yeah, if x equals t squared, dx is 2t dt. And if y is t to the third, dy is 3t squared dt. So the d parts always come from the derivatives of your path that you have. Now, so I would have to do that. I had to parameterize all 4 of these line segments and do a separate calculation of 4 different line integrals one at a time to get that total value and add up the results when I'm finished. Green's theorem is going to offer you something different, okay? When you come across these line integrals that have the dx dy type, and your path is actually a closed loop, like this. In other words, you probably never heard have you ever heard the word closed in reference to a curve before? Closed curve versus open curve, I guess, or any closed curve is basically any curve that doesn't overlap with itself, but eventually its end point and beginning point are the same point. So there's a distinct interior and exterior that it splits 2D or 3D into. Okay, so in this case, there's an inside, there's an outside, there's a loop there. So Green's theorem applies. So notice it uses some of the same notation that I showed you earlier in the fundamental theorem. P here represents the function that's paired with dx, and Q represents the function that's paired with dy in that same alphabetical order. So see, in this line integral we're going to evaluate, P is the 2 minus y squared, and Q is the xy. So make those pairings, hopefully pretty obvious. Because in order to use Green's theorem correctly, what you do is, where C represents the curve that wraps around some domain or region D in the plane, you can turn this into this double integral. Test 3. And the integrand of your double integral comes from taking Q's partial with respect to x and subtracting P's partial with respect to y. Green's theorem is very tough to prove. It's a very lengthy proof. So I don't want to say it's beyond the scope of our class, because obviously we're using it in here, but